S of x and S of y, so along the x component and the y component. And interestingly, you can calculate that. So I should just do that, and you find that the eigenvalues are also plus or minus h over 2. Things are so simple, I guess there's not much possibility for variation, right? And if you calculate the eigenvectors for them, you'll get these. So I'll put that as homework. Do that. So you know the 2x2 matrices, the Hermitian matrices for S of x, S of y, and S of z. So you can find their you can write out their eigenequations, and then and because these matrices are just 2x2, very easy. So you can solve them readily for the eigenfunctions and the eigenvalues, and you find the eigenvalues come out to be both for S of x and S of y. So this would be the value of the spin angular momentum along the component along the x-axis, and similarly for the y-axis, right? And you get the same eigenvalues as you got for S of z, and you get them also for S of x and S of y. It works out in this case, right? And solve for the eigenfunctions, the eigenvectors, and you'll get these values. Now you get this for when it's plus h over 2, and you get this for when it's and you get this for when it's minus h over 2. And if you're talking about the y component, it's the eigenstate is this for when the eigenvalue is at plus h over 2, and it's this for when the eigenvalue is minus h over 2, right? So do that for homework. Do these homeworks to get familiar. When you're actually calculating it yourself, you have to think harder. So problem solving is very useful for understanding. Alright, now so we have these eigenstates. How about so if we took like two of them, what in this context now of 2x2 spin matrices and their eigenstates, how would you define, what's the meaning of the what we had earlier as brackets, the bra and the ket? Well, so a bracket. So if we wanted to normalize, for example, to find a normalization constant. So in this context of 2x2 spin matrices, how do you define bracket? If you take a spinner, like here's a spinner, right? So if that's your ket, what's the bra? Well, let it be that. Seems sort of a natural suggestion, right? Because if you take a bracket of a spinner, if the bra is of the same spinner as the ket, then you want to get something that's a real number, right? Like 1. So it makes sense to these in general. A spinner consists the elements of a spinner, column vector, complex numbers. So if you're going to take a bracket and you want it to come out as a real, it makes sense that you want to conjugate your spinner, the ket, into the bra. So the bra form here, you just conjugate. Okay, so that if you're trying to find the bracket of psi, do it this way, where psi, well, this ket here is a spinner, right? 2x2, a two-component spinner. And, well, it's just matrix multiplication, right? You multiply this matrix by that matrix and you get a squared plus b squared. Choose a to normalize your spinner such that so it's 1, right? And if you do that, if you normalize your spinners, then these various spinners, they are orthonormal. And do that for homework, right? Show, that's pretty trivial. That's not difficult at all. And you probably see it just by inspection that Now if you multiply that by that, you'll get 0. Does that make sense? If you take the bra of that and the ket of that, you'll get it'll come out to be 0. And similarly, does that make sense? 1 by 1 is 1, and you're conjugating it, so minus I times minus I, so that's plus I squared, which is minus 1, which cancels with a 1, so you get 0. Yeah, you just do that almost by inspection. Okay, so these eigenfunctions, or these spinners, if you like, are orthonormal, so do that also for homework. Okay, so a bit of a note here before getting onto a new topic. When you're talking half integer spin, half integral angular momentum, if you like, L is a half. You can't use this kind of thing. You can't use your spherical harmonics because it's just not applicable. Because if you use your spherical harmonics, you end up proving your L is integral. But that's not what we're doing. So we can't use this. So virtually all we can use is the matrix and vectors, spinners approach. So quite a few sessions back I was saying that instead of using operators and wave functions and so forth, when it comes to spin, it's more convenient to use matrices. In fact, it's more than just convenience, you have to, right? Which is what it's saying here. Right, now I put the heading here just because it has some space, but the next topic is, I'll give you the general idea before we get into the details in the next session. Talking 2 by 2 matrices, spin matrices, because these matrices are so small, so simple, just 2 by 2, then they're a very useful and convenient and easy way using them in the context of spin, where we're not caring about the motion of the particle. Let's say our general wave function is just about spin and only spin. There's only 2 eigenstates, right? Up, spin down. Arrow, ket with the arrow up, ket with the arrow down. There's only 2 eigenstates. So your general form, your general spinner, will be C1 spin up state plus C2 spin down state, and that's a very simple generalized superposed wave function in the context of spin, and we can illustrate a lot of the principles, the basic principles, like from the previous chapter, chapter 6, using spinners and spin matrices and so forth. So that's the topic of the next session.